Today, we are going to see the third experiment on-off control of a thermal process or temperature process. To control this water bath, we are having a heater. A heater is placed inside this water bath to measure the temperature. A PT100 RTD is used. So the RTD is a passive device. Its resistance will change based on the temperature. Here, the maximum temperature is 100 degrees centigrade. So it varies from 0 to, let us assume that it varies from 0 to 100 degree centigrade. So that resistance has to be converted into a voltage or current. For that, a signal conditioning circuit is required. Circuit is required. Here, change in resistance is converted into 0 to 5 volt. That is given to a on-off controller. The set point is given to that on-off controller. The output of this on-off controller will on-off controller will on or off this heater. Depends upon this temperature. Suppose the set point is 60 degrees centigrade, means whenever it exceeds 60 degrees centigrade, it will turn off. Whenever it is below 60 degrees centigrade, it will turn on. That is the idea. So the first step is we have to design the signal conditioning circuit that will convert the change in resistance into 0 to 5 volt for the given range. The physical range is 0 to 100 degrees centigrade. Transducer, the signal conditioning circuit output must be 0 to 5 volt. Here, the resistance at a particular temperature RT equal to R naught multiplied by 1 plus alpha delta T, where R naught is the, for a PT100, R naught equal to 100 ohm at 0 degree centigrade, alpha equal to 0.0038 ohm per degree centigrade. Yes. So if you substitute, the maximum temperature is 100 degrees centigrade. If you substitute 100 degrees centigrade, then change in temperature is 100. That's why RT, R100 equal to 138 ohm. R0 equal to 100 ohm. We have to design a signal conditioning circuit to convert this change in resistance of 100 to 138 into 0 to 5 volt. So for that, let us have a Wheatstone bridge circuit. This is of 100 ohm. This is also of 100 ohm. The third arm also 100 ohm. Here we are having that RTD. RTD. So here it is connected to ground and this is at plus 5 volt. The output is available here. What is the bridge output? How to find that? The current through this path is at 100 degrees centigrade. The resistance is 138. Therefore, current through this path, this is at ground potential. This is at ground potential. Therefore, current equal to 5 divided by 100 plus 138, 238 multiplied by the voltage at A equal to the drop across this RTD, that is 138 minus, this is VA. This is at B. VB is equal to what? VB is equal to applied voltage is 5 divided by the 2 ohm resistance is 200. Potential at B is drop across this 100 ohm, bottom 100 ohm. Therefore, multiplied by 100, that is equal to 138 divided by 238 minus 5 by 200 multiplied by, 100 by 200 multiplied by 5 equal to 0.4 volt. At 0 degree centigrade, at A, the potential is 2.5 volt. Potential at B also 2.5. That is 100 divided by 200 at 0 degree centigrade at 100 degree centigrade minus 100 divided by 200 multiplied by 5 equal to 0 volt. Therefore, the span is 0 to 0.4 volt. The input span of signal conditioning circuit is 0 to 0.4. That has to be amplified to the output of signal conditioning circuit span must be 0 to 5 volt. Therefore, gain of the amplifier equal to 5 minus 0 divided by 0.4 minus 0. 5 by 0.4 equal to 50 by 4, 12.5. So we will design VA, VB will be connected here to an op-amp, which is at higher potential. VB always at 2.5 volt. VA increases up to from 2.5 to 0.4. VA increases always while giving to the differential amplifier. Higher potential must be given to positive terminal. Higher potential must be given to positive terminal. That's why VA should be connected here and VB should be connected here. Even though it is a differential amplifier, to get the positive output, higher voltage must be given to positive terminal. So it is a differential amplifier. Let us assume that the feedback resistance is 12.5 kilo ohm. Let it be, the input resistance is 1 kilo ohm. .5 kilo ohm. So here you will get 0 to 5 volt for a temperature of 0 to 100 degree centigrade. Why can't you use common mode amplifier? If you use that, this end is grounded. This end is grounded. This end is grounded. That's why you cannot ground the reference B. That's why we need a differential amplifier. Its output is 0 to 5 volt. Now we have to draw the calibration curve. We have to check whether it gives 0 to 5 volt or not. For that, you vary the temperature of the water bath from room temperature to, say, room temperature is 30 degrees centigrade to 100 degrees centigrade. For that, the voltage you got, you can plot this. You can plot like this. This is the calibration curve for 5 volt. This is 1.5 volt. So you'll get the calibration curve is required. Suppose you want to control at 60 degrees centigrade, means you have to check what is the output of this circuit for 60 degrees centigrade. Say 3 volt. Ideal case, you'll get 3 volt for 60 degree. If it is 0 to 5 volt, means you'll get 3 volt for 60 degree. That is, you have to note down. So we have to control for 3 volt. So what is this RTD is connected here. The output of this bridge is 0 to 0.4. That is given here, the differential amplifier. This part is signal conditioning circuit. The output is 0 to 5 volt. This is the process variable. Now we have to generate a set point for that controller. To generate set point, let us take a pot, give plus 5 volt and ground this end. You will get 0 to 5 volt here. That is set point. That is set point. Now we have to design the on-off controller. Process variable is available in the output of this signal conditioning circuit. That is 0 to 5 volt. That should be given to a op-amp, open loop op-amp. If it is open loop, means this is plus and minus. The set point is given to positive terminal of op-amp. And the process variable 0 to 5 volt is given to inverting terminal. Process variable 0 to 5 volt. What is the output of this open loop op-amp? Whichever is higher, it will saturate that voltage. Suppose set point is higher, means it will saturate to plus 12 volt. If set point is greater than process variable. In other words, V plus is greater than V minus, it will saturate to plus 12 volt. If this will saturate to minus 12 volt, if V minus is greater than V plus, or process variable is greater than set point, it means it crosses 60 degrees centigrade. Or that's all. So the output is either plus 12 volt or minus 12 volt. This is on, this is off. That's all. So we got the on-off controller. On-off here, the open loop op-amp acts as an on-off controller. Set point is generated by this part. So you can adjust this part so that here you can give 3 volt as set point for 60 degrees centigrade. So here the output will be 12 volt or minus 12 volt. Now we have to turn on the heater by using 230 volt. For that, we are going to use a relay circuit. There are 2 types of relays. One is electromechanical relay. Electromechanical. This is old one. Another one is nowadays, it's available in solid states. Solid state relay is available. Or solid state switch, you can call it as. Relay or switch. So if we are going in the lab, we are going to use that old one, electromechanical relay. The electromechanical relay is, inductor, electromagnet, and two contacts will be there. If we energize this inductor, this will close, that's all. It acts as a switch. Normally open. This is called a normally open. If you energize, it will be closed. That's why it is called normally open. This here, another switch is there, but we are not going to use that. That is normally closed. This side, it will be there. We are not going to use, that is called normally closed. If we energize, it will open. So both can be used. We are going to use normally open. Here, we'll give a phase 230 volt, single phase. Power supply will be given here, and it will be taken here, and it will be connected to the heater. The other end is connected to neutral. So this is the heater immersed inside that water. So this relay has to be turned on and off, depends upon this plus 12 volt and minus 12 volt. 12 volt means it has to be turned on. You cannot connect this op-amp output directly here. If you connect the 12 volt power supply here, this will energize. But this op-amp, it's not good to connect directly because it may not source that much current, because it requires, it is a 200 ohm resistance. This coil has a resistance of 200 ohm. Therefore, the coil requires current equal to 12 volt divided by 200 ohm. That is equal to 60 milliampere. It cannot source that much current. That's why you cannot connect directly. So you have to put an amplifier in between the two. 60 milliampere is required. So we'll put a SL100 here, amplifier. The collector is connected, one end, other end is connected to plus 12 volt. This end is grounded. So this collector, whenever a 12 volt is available, this collector will permit a current of 60 milliampere. It has to permit a current of 60 milliampere. If this is base, if you connect this, if it is 12 volt, what will happen? Here we have to resist the base current. For that, one resistance RB is connected. Plus 12 volt means this will be forward biased. That's why it will source a current of 60 milliampere. Minus 12 means it is not forward biased. Base emitter is not forward biased. That's why it will be turned off. So this SL100 will act as a switch. This SL100 will act as a switch. We have to find RB. The gain, current gain, beta of SL100 is 99. Say 100, approximately equal to 100. Therefore, we have to find RB. We know that IC equal to beta times IB. Beta times IB, that is 100. Therefore, IB equal to IC, that is 60 milliampere is required, divided by 100. Beta is 100. Therefore, IC by beta equal to 0.6 milliampere. So base current, whenever the base current is 0.6 milliampere, then it will be turned on. Less than 0.6 milliampere, it won't turn on. So to get 0.6 milliampere, 12 volt is there. The other end of emitter is grounded. Therefore, RB equal to 12 divided by, let us ignore the drop across the junction, that is 0.7 volt, drop across the base emitter junction, that 0.7 is ignored. Or you can put 12 minus 0.7, that is also possible. 0.6, 12 by 0.6 equal to 20. 12 by 6 equal to 5. 20. 12 by 6 equal to 2. 12 by 0.6 equal to 20. This is milliampere. That's why 20 kilo ohm. So you'll get 20 kilo ohm. This RB equal to 20 kilo ohm. RB equal to 20 kilo ohm. So here, the output of this bridge circuit is connected here. That is amplified to 0 to 5 volt. That is connected to this on-off controller. This acts as on-off controller. On-off controller. So that will drive this SL100 so that this will be turned on and off. Here, suppose you want to control at 60 degrees centigrade means from the calibration curve, 60 degree corresponds to 3 volt. May not be exactly 3 volt. Theoretically, it is 3 volt. You have to check in the graph. That voltage is given here. That voltage is given here, say 3 volt. So what will happen? Initially, it is at room temperature. That's why 30 degrees centigrade means it will be 1.5 volt, which is higher. 3 volt is higher. That's why output is 12 volt. That's why this will be turned on. The heater will be turned on. The temperature will go on increase. The temperature will go on increase. The set point is 60 degrees centigrade. Whenever just it crosses, it is greater than say 3.01 volt. So this is higher. That's why it becomes minus 12 volt. That's why it will be turned off. But anyhow, there will be a slight increase due to inertia that already we have discussed. Due to inertia, it will go up, then go down. Whenever it falls below that 60 degree, again it will be turned on. So it will be like this. It will wander around 60 degrees centigrade. It will wander around 60 degrees centigrade. That's all. About on-off controller, this you have to do in the laboratory.